This is synopsis on gravitation. First topic, Newton's law of gravitation. The force of attraction or repulsion between two point masses is proportional to product of the masses and inversely proportional to square of the distance between the masses. Okay. If m1 m2 are point masses, distance is r, then g m1 m2 by r square. Simultaneously compare this with electrostatics. The force of attraction or repulsion between two point charges, here it is always attraction. Two point charges is constant q1 q2 by r square. Okay. Here g m1 m2 by r square. So force of attraction between two point masses is directly proportional to product of the masses, inversely proportional to square of the distance between them. This force is always attractive. For that reason, we can also write minus into r cap. Minus sign says attractive force. The meaning of point mass. The meaning of point mass. If dimensions of the object, dimensions means length, width or thickness of the object, is very small compared to distances. Okay, here is another mass. If distance between these two is large compared to length or width and thickness of the object, then we can treat these two as point masses. And unit of SI unit of G is force into distance square, Newton meter square, mass kg square per kg square. Newton dimensional formula, Newton is mLt minus 2, L2 is meter square, kg m minus 2. Okay. When we simplify, m minus 1, L3, t minus 2. This is the dimensional formula for G. This is the SI unit, Newton meter square per kg square. Next, second, Kepler's laws. Kepler's laws of planetary motion. Laws of planetary motion. There are three laws. First law says all planets revolve around the sun in elliptical orbits with sun at one of its foci. If this is sun, there are two focus for an ellipse, singular focus, plural foci. If sun is at one of the foci, then planets revolve around the sun in elliptical orbits. This is first law. Second law says if this is an elliptical orbit, sun, planet, this is imaginary line joining planet and the sun. Planet and the sun. In 1 month, if planet moves some distance, then this imaginary line sweeps some area. This is the area swept by the imaginary line. If planet is closer to the sun, then it moves some distance in 1 month such that the imaginary line sweeps area equal to this area. So this area equal to this area. Observe carefully. In 1 month it travels lesser distance if it is away from the sun. If it is closer to the sun, planet is closer to the sun, it moves or it covers more distance. Means orbital speed is more if it is closer to the sun, orbital speed is less if it is away from the sun. Observe length of the arrow. Magnitude is proportional to the length. Here magnitude is less, therefore shorter length, shorter vector. Here magnitude is more, that is why it is shown by this longer vector. Okay. So imaginary line sweeps equal areas in equal intervals of time. This is due to law of conservation of angular momentum. Angular momentum. Angular momentum. Next, third, square of time period of revolution of a satellite is proportional to cube of semi-major axis. If this is an ellipse, this is major axis, this is minor axis. half of the major axis is semi-major axis, half of minor axis is semi-minor axis. So here square of the time period of revolution is proportional to cube of the semi-major axis. So this is also called law of periods. This is law of areas. So this is Kepler's laws of planetary motion. Based on t square proportional to a cube, a satellite in a circular orbit of radius r has a time period of 4 hours. So t square is proportional to a cube. Okay. Time period is 4 hours. Square is proportional to r cube. Next, another satellite with orbital radius 3r. 3r cube is proportional to this time square. Time period of revolution square is proportional to 3r cube. If we divide one by the other, r cube get cancels. 3 cube is 27. 4 square into 27 equal to t square, or t equal to, take square root 4, this is square root of 27, so 4 root 27. So based on this equation. Next topic, acceleration due to gravity, denoted by g. Acceleration due to gravity. This is also called force per unit mass. Force per unit mass. Okay. So more appropriate is force per unit mass, or commonly used acceleration due to gravity. If this is the earth and capital R is mean radius of the earth and mass of the earth m, there is an object on the surface, means this object is pulled by gravitational force given by g m by r square. Mass of the earth, mass of the object, distance square, distance between these two centers, is equal to, from Newton's second law of motion, this mass is pulled by some force, therefore we can write m into g. M get cancels, therefore g equal to gm by r square. So this is the expression for acceleration due to gravity. Observe, this is from Newton's law of gravity, Newton's law of gravitation, and this is Newton's second law of motion. Both the forces are same, magnitudes are same, but the interpretation is different. Okay. Now force equal to g m by r square. Take this m to this side, so F by m is nothing but small g. For that reason, g is also called force per unit mass, gm by r square. Okay. Now, fourth, variation of g with height. Variation of g with height. If this is the earth, mean radius of the earth, mass of the earth, acceleration due to gravity on the surface is g m by r square. Acceleration due to gravity at some height h, g prime equal to gm by r plus h whole square. When we divide one by the other, we get g prime equal to g into r square by r plus h whole square. So with the increase in h, acceleration due to gravity decreases. This equation can be used for any heights. Okay. If height is very much smaller than the radius, then this equation can be approximated to g into 1 minus 2h by r, where h is height, mean radius of the earth, acceleration due to gravity on the earth. This is acceleration due to gravity at height h. Be careful. Warning, this equation is true only if h is very much smaller than r. Meaning, if h is about 25 km or 100 km, then you can use this equation. If h is greater than 100 kilometer, then the error increases. That is why we should use this equation. So this equation for any height, whereas this equation for h very much smaller than r. This is variation of g with height. With the increase in height, acceleration due to gravity decreases. Next, fifth, variation of g with depth. Variation of g with depth. If this is the earth, mean radius of the earth r, mass of the earth m, acceleration due to gravity on the surface g equal to gm by r square at some depth d. If this is depth d, then acceleration due to gravity at this depth is given by g into 1 minus d by r. So this equation is true for any depth. Okay, there is no condition. If d equal to r, what do you mean by d equal to r? If depth equal to r means at the center of the earth, at the center of the earth, put d equal to r, we get g prime equal to g into 1 minus r by r get cancels, 1 minus 1 0, therefore g prime equal to 0. Acceleration due to gravity equal to 0. So with the increase in depth, g decreases. With the increase in height, g decreases. Next, sixth, variation of g with latitude. This is required from competitive exams point of view, but this is not there in the syllabus. Okay, if this is the earth, equator, axis of rotation, angular velocity omega, this is equator. Any object on the equator experiences two forces or two accelerations. One is acceleration due to gravity towards the center, the other is centrifugal acceleration. If object is somewhere here where its latitude is theta, so this is how latitude can be found. Therefore latitude for equator is 0 and at poles theta is 90 degree. Okay, fine. At some height, at some position where latitude is theta, this object, when earth spins, this object will be moving along the circumference of this circle. Therefore this object experiences this small centrifugal force, whereas there is large gravitational pull. This is centrifugal acceleration. This is acceleration due to gravity. Here g prime equal to g minus a. Here also g prime equal to g minus r omega square cos square theta. So this is the equation to find acceleration due to gravity. This is due to the component of centrifugal force in this direction. Let me repeat. This second term r omega square cos square theta is due to component of this centrifugal acceleration in this direction. Okay, when we simplify that, we get g minus r omega square cos square theta, where r is mean radius of the earth, omega is angular frequency of rotation of the earth about the axis, theta is the latitude. Along the equator, theta equal to 0 degree. If theta is 0, cos 0 is 1, therefore g prime equal to g minus r omega square. G prime, or acceleration due to gravity, is minimum. It is minimum because r omega square plays a role. At poles, theta is 90 degree, cos 90 is 0, therefore g prime equal to g. So at poles it is maximum. Along the equator, it is the acceleration due to gravity is minimum. This is variation of g with latitude. Okay. Now let me denote it again. At poles, acceleration due to gravity is maximum. Along the equator, acceleration due to gravity is minimum. Okay. Next, seventh, orbital velocity of a satellite. If this is the Earth, mean radius of the Earth, mass of the Earth, this is some satellite at a height h, then this satellite is revolving around the Earth with uniform velocity. This is the velocity vector, this is orbital velocity, and expression for orbital velocity is root of gm by r plus h. So orbital velocity depends on height. Orbital velocity depends on height. Close to the Earth, h is approximately 0. Okay, if h is approximately 0, or r plus h is approximately equal to r, then orbital speed is about 8 km per second. So it's better to remember these numbers. Okay, very close to the Earth, orbital speed is about 8 km per second, and with the increase in h, orbital speed decreases. So this is the expression for orbital speed. 4 terms: g, m, r, and h. Okay. Next, eighth, escape velocity. Escape velocity denoted by VE equal to root of 2 gm by r. From the surface of the Earth, some object is thrown such that the object should not return. Then kinetic energy given to the object should be equal to gravitational potential energy. After simplification, we get escape velocity equal to square root of 2 gm by r, or it is also equal to square root of 2 g r. If there is nothing in the denominator, then this is small g. If it is capital G, then there is a term in the denominator. Okay, be careful. Small g is acceleration due to gravity, capital G is universal constant of gravitation. So this is the expression for escape velocity. Next, ninth, gravitational potential energy. Okay, if this is the Earth, mean radius r, mass of the Earth m, then potential energy is given by minus g m by r plus h. Compare this with electrostatics. Potential energy of a system of two charges is constant q1 q2 by r. There is no square, q1 q2 by r. This is the expression for potential energy. It is 1 by 4 pi epsilon naught. Whereas in gravitation, it is attractive potential, that is why negative sign is used. mm by r plus h. This is also equal to minus mm by r. Small r is r plus h. Okay, gravitational potential energy. Similarly, we can write expression for kinetic energy. Kinetic energy at some height. If this is the Earth, here is a satellite moving with velocity v0, orbital speed, then kinetic energy is given by half m v square, this is orbital velocity square, which is equal to half mass of the object, orbital velocity square. Orbital velocity has square root of gm by r plus h, its square. Therefore, half m gm by r plus h. Okay, so this is expression for kinetic energy. We have one more expression for potential energy. If h is very much smaller than capital R, then potential energy is also equal to mgh. So this equation we use more often in work, energy and power chapter, isn't it? mgh. Whereas this is for any height. This is if h is very much smaller than r. Okay, gravitational potential energy. Next, 10th, time period of revolution. Time period of revolution of a satellite. Okay, this is the Earth, mean radius, mass. If this is a satellite, this satellite is revolving around the Earth. Height of the satellite is h. Then time period of revolution is given by 2 pi r plus h whole to the power of 3 by 2 divided by square root of gm. It's a bit weird equation, but it's actually a beautiful equation. See, 2 pi r plus h whole power 3 by 2 by square root of gm. This is time period of revolution, and we also know frequency of revolution is reciprocal of time period of revolution. So we can take the reciprocal and write the equation. Okay, it doesn't matter. And also observe, as h increases, time period of revolution increases, and very close to the Earth. Time period of revolution is about 1.5 hour. It is 1.5 hours. And for a geostationary satellite, time period of revolution is 24 hour, and height is about 36,000 kilometer. Okay.